In this part of chapter 13, we are going to discuss reaction quotient. If a reaction mixture containing both reactants and products, but equilibrium is still not established in the mixture in this reaction, how can we determine in which direction it will proceed? How can we determine the sign of changes in concentrations of reactants and products? To answer is to compare the current concentration reactions to the equilibrium constant. For this purpose, we need to set up expression for the reaction quotient, which is at the first glance is absolutely the same as expression for equilibrium constants, with only one difference. Instead of equilibrium concentrations, in expression for reaction quotient, we have to incorporate current concentrations of product and reactants, which are not equilibrium concentrations. And if reaction is established for gases, it proceeds in a gaseous phase, and we are provided with partial pressures. In this case, the reaction quotient will be represented as Qp. An expression for this case is right in front of you in this frame. Let us see what cases are possible when we compare value of quotient and equilibrium constant. If quotient greater than K, then reaction will proceed faster in the reverse direction. Hence, it means that concentration of products will decrease and concentrations of reactants will increase. When we analyze our ice table, the sign for changes in concentration of products is going to be negative, and for reactants is going to be positive. And opposite, if quotient is smaller than K, the reaction will proceed faster in the forward direction. What it means? It means that the products will increase in amount and has to be designated this change with positive sign, and concentration of reactants will decrease, and changes in concentration of reactants has to be negative. If quotient equal equilibrium constant, it means the reaction is at equilibrium. And here it's very important to understand that the concentrations of products and reactants are not going to change, and the rates of the forward and reverse reactions are the same. If reaction mixture contains just reactants, quotient is going to be 0, and the reaction proceeds in the forward direction. And in opposite, if a reaction mixture contains just products, quotient is infinite, and the reaction will proceed in the reverse direction. Let us try to represent cases which we discussed in the previous slide using a graphical diagram. So this is a borderline which illustrates equilibrium when quotient equal equilibrium constant. This is a K. This diagram has two sides. The left side is the quotient smaller than equilibrium constant, and the right side when quotient is greater than equilibrium constant. The left side is the side of reactants, and the right side is the side of products. If our reaction is a ball which is going to fall down in a forward direction, it will start to move, and the rate of this movement will increase. So hence concentrations of reactants will decrease when reaction proceeds forward. And an opposite, if the ball is on the right side and it's going to move in a reversed direction, the concentrations of products are going to decrease. Excuse me, going to decrease. Let us see how can we apply the concept of quotient for a particular question. We are given reaction and we need to figure out which direction will it proceed if partial pressures of reactants and product are given. Please remember, partial pressures might be incorporated in equilibrium constant expression as well as in quotient expression, the same way as we have done it for concentrations, and it's the analysis and the strategy for analysis is absolutely the same, totally the same. We need to understand in this problem that these partial pressures are not equilibrium partial pressures. These partial pressures are at some moment of time. First step which you need to take is to set up equation for the quotient. An equation for the quotient based on expression for reaction between iodine and chlorine we have in this area. This is expression for the quotient. Then we just need to plug in numbers which are provided for partial pressures and literally calculate quotient. And the last step which you need to take is to compare quotient, value of quotient, magnitude of quotient, and equilibrium constant. And based on the comparison, we can see that quotient is smaller than equilibrium constant. Hence, it means that reaction will proceed to the right. Let us do this practice. We have results of 3 experiments, experiment 1, 2, and 3. And the results of these experiments in terms of concentrations are represented in this table. So we are required to figure out for each of the following measured concentrations where the reaction is at equilibrium. We need to analyze quotient, we need to compare quotient, we need to calculate quotient and compare quotient versus equilibrium constant. If reaction with represented concentration is not at equilibrium, we need to predict in which direction will the reaction proceed to get to equilibrium. So the first step which we need to take, we need to set up expression for the quotient. So expression for the quotient will be based on an equation, the concentration of carbon disulfide times concentration of hydrogen power 4 over concentration of methane times concentration of hydrogen disulfide, dihydrogen sulfide or hydrogen sulfide squared. And now we just need literally plug in numbers and compare this number versus the result for equilibrium constant, which is given right here. So it's right here in front of us and we need to compare it with this number. Okay, so let us do the first experiment. So quotient, experiment 1. So, and just carefully, thoroughly watching numbers, let us plug in them into expression times 1 or 8 power 4 divided by 115 times 120 squared, and the first result is 1.24. When we compare this quotient with equilibrium constant, we see that it's smaller than Kc. So hence, in this case, we need to say that reaction will proceed forward. Reaction proceeds forward. In second experiment number 2, the result, we need to again plug in numbers, and the result is going to be 586, which is greater than Kc provided. It means that reaction proceeds backward. In the third case, when we calculate it for the third experiment, you will see it's 3.59, which exactly as equilibrium constant. Hence, reaction is at equilibrium.